Hi, it's me, Tim Dodd, the Everyday Astronaut. This is SpaceX's Raptor engine that powers their Starship and Super Heavy booster. When this thing is running, there is unbelievably hot combustion continually burning at the heart of this beast. In fact, the gases inside the combustion chamber can reach about 3,500 Kelvin, about half as hot as the surface of the sun, which is above the melting point of pretty much any material out there. But this heat is kind of what makes a rocket engine function. I mean, after all, their only real purpose is to convert the chemical energy inside the propellant into pressure, and often therefore heat, so that they can produce thrust. And that brings up an obvious question. How in the heck do engines survive this heat? How did rocket scientists figure out how to keep an engine running continuously while harboring combustion inside that's hot enough to not just melt the metal walls containing it, but actually vaporize the metal, or more pedantically, sublimate the metal from solid to a gas in an instant? But we'll just say melt for simplicity in this video. So today, we're going to talk about the tricks engineers employ to keep rocket engines from melting. Here's the timestamps to the sections we're going to be going over, such as heat sinks, fuel to oxidizer ratios, ablative cooling, regenerative cooling, film cooling, and radiative cooling. And we're also going to be showing you some awesome examples of each of these as well. And if you're someone who would rather read about this instead of hear me talk about it, don't forget we do have an article version of this up at our website at everydayastronaut.com, and there's a link in the description to that article. Rocket engines. Too cool to melt, but how? Let's get started.
3, 2, 1, liftoff. That's one small step for man. Contact with a test one.
This is a combustion chamber. At the top of it is the injector face. This is where the fuel and oxidizer get pumped into the chamber at very high pressures. The fuel and the oxidizer will mix somewhere downstream of the injector face inside of the combustion chamber, and they'll ignite and then combust. Assuming there's adequate and continuous flow, the propellants will burn. But with ridiculously hot gases squeezed together in between the metal chamber walls, we certainly don't want the metal to melt. So perhaps the easiest thing we could do is just make the metal walls so thick, even the scorching hot gases can't heat up all the metal enough to actually melt it. The walls act as what's known as a heat sink, or a giant thermal conductor that can handle a high heat load for a period of time before it warms up all of the metal to its melting point. The use of exotic materials might be a fitting choice here, something that can handle extreme heat and still be strong, such as Inconel or other alloys, but of course, price or weight or other factors certainly come into play. Obviously, first off, if you're using thick metal walls as a heat sink, they're going to be quite heavy. And in a world where rocket engineers would eat a hat for even a 5% weight reduction, making your engine's walls so incredibly thick they don't melt is not only far from optimal, it's downright primitive. The other problem is you can realistically only run an engine for so long before you eventually heat it all up to its melting point, so it has inherent limitations and viability. This option isn't a very good choice for main propulsion engines, where they might need to run for several minutes continuously. But this option is actually valid for smaller engines, such as reaction control thrusters. Reaction control thrusters are often pulsed and run in shorter duration burns. This allows them an opportunity to cool down between pulses. This keeps them simple and reliable, but with limitations on continuous runtime to keep them from melting. But what if you could just lower the temperature of the combustion? A less hot gas might make it so you could use thinner walls, and might make long duration burns more survivable. Well, that actually is an option. The next relatively simple thing you can do to keep your engine intact is to simply run the engine with more fuel or more oxidizer, otherwise known as fuel-rich or oxidizer-rich, which can lower the temperature of the exhaust. This ratio is the fuel to oxidizer mass ratio. Now, if you wanted to burn 100% of your propellant and have absolutely as much of it react with each other as possible, you'd need to burn it at what's known as its stoichiometric ratio. This is where there's the exact amount of fuel and oxidizer to perfectly react as completely as possible with each other, which leaves no propellant left unburnt. But burning at your stoichiometric ratio also means you're releasing as much heat from the chemical bonds as possible too. While that might actually be ideal in some situations, That is not ideal in a rocket engine for a few reasons. The more heat your engine is producing, the more you need to cool your engine via other methods, so it doesn't melt, and you're going to need to employ more of the tactics that we're going to be discussing in this video. So rocket engines need to run their fuel to oxidizer ratios a bit off from stoichiometric. Main combustion chambers tend to run fuel rich because this usually results in lower thermal loads and higher efficiency. Not to mention, scorching hot gaseous oxygen is typically avoided as much as possible, since it sure loves to turn metal into soup, and the rocket engine will end up running engine rich, and that's definitely not good. But beyond just the main combustion chamber's fuel to oxidizer ratio, you can also run your preburner or your gas generator very fuel rich or oxidizer rich in order to keep it cool too. In fact, you can burn it at a different, more conservative, cooler temperature than you would your main combustion chamber. And quick side note, if you don't know what a preburner is or a gas generator, don't worry, I've got you covered. Check out my Soviet rocket engine video. In the beginning in the glossary, I go over a lot of terms that will be really helpful for this video and frankly, all videos about rocket engines. Okay, back to keeping your preburner or gas generator cool with your fuel to oxidizer ratio. This is extremely important because it's hard to cool a spinning turbine. You're really stuck with a set amount of heat that it can actually take based on the materials. And you just kind of simply have to change your fuel to oxidizer ratio until the heat load is bearable. And unlike the fuel-rich main combustion chambers, turbines can be designed to run fuel-rich or oxidizer-rich. For example, the Space Shuttle's RS-25 main engines ran fuel-rich through their preburner, while the Soviet-designed NK-33 ran oxidizer-rich propellant through their closed-cycle preburners. But all of this is rocket science we're talking about, and performance and optimization is everything. So we don't want a big, heavy engine or one that's sandbagging its performance to run cooler. But we also don't want our engine to melt. Or do we? Welcome to perhaps one of the most simple and effective ways to cool an engine. And that is, well, to allow it to melt, but just a little bit. This is called ablative cooling. Ablative cooling is where you use a material that will vaporize and gets thrown into the wake, which takes the heat along with it. It's most commonly made out of carbon composites, which have a very high melting point. This is also the same principle many spacecraft use on their heat shields. When a spacecraft is coming back into the atmosphere for re-entry, it gets crazy hot. And the heat shield just accepts that heat. It takes it right in the face. And then when the surface gets too hot, it basically melts a layer away, taking the heat with it. This prevents heat from penetrating deeper into the vehicle. And this is the same idea you can use to cool a rocket engine. Inside the metal walls of the combustion chamber and the nozzle will be a layer of carbon composites. As the propellant burns inside the engine, the carbon liner will slowly get chewed away. Now, if you're anything like me, you might think this sounds like kind of a terrible idea. But it's actually an incredibly efficient and reliable method of cooling since it's self-regulating, has no moving parts, and is incredibly effective. But it does have its limitations. Obviously, if you're looking to reuse your engine, you should probably look elsewhere. In fact, some engines may not be able to go through their full testing before use because it will wear down the ablative chamber walls. And because the chamber and throat walls get thinner, their performance can actually decrease throughout the burn, as your throat's area will increase a lot compared to the nozzle exit, which will decrease the overall expansion ratio of the engine, which is the opposite of what you want as you ascend into thinner parts of the atmosphere. And it's also quite heavy. The ablative material is just extra stuff that weighs a decent amount. Perhaps one of the most famous examples of this is the Apollo lunar ascent engine, which could not be test fired as a complete unit before being lit on the surface of the moon to get astronauts home. Yes, that's a terrifying thought. Some other examples of ablatively cooled engines are SpaceX's first Merlin engine, the Merlin 1A, which flew on the first 2 Falcon 1 flights, and United Launch Alliance's Delta IV engine, the RS-68A. On the RS-68A, you can easily tell this engine is ablative because The engine runs on hydrolox, which usually has a nearly completely transparent exhaust of just water vapor like we saw on the space shuttle. But the RS-68A's exhaust is bright orange because the carbon that is ablated and ejected from the engine continues to react with the oxygen in the atmosphere, which makes it burn bright orange. Sometimes reaction control thrusters use ablative chambers too, since they are often used in short durations and have a set amount of propellant they can use before they run out, so engineers can design the wall thickness to match the maximum use case. Okay, but what if ablative cooling is just not cool enough for you? Well, then we've got a few more options to check out. Perhaps the most common way to keep a liquid-fueled rocket engine from melting is by using regenerative cooling. This is where they flow some or all of the propellant through the walls of the combustion chamber and the nozzle before it goes through the injectors and into the chamber. Yeah, that's right. Even though the walls and the nozzles of rocket engines look super thin, there's often a very small channel where fuel can run up and down the walls in order to keep them cool. This was a major breakthrough that allowed rocket engines to run more or less indefinitely. Early versions of regeneratively cooled engines would have the main chamber and then basically a liner on the outside of it to run the coolant or fuel through. Later, it became common to actually just use pipes to form the walls of the combustion chamber. In fact, the RL-10 engine still uses brazed tube construction today, although they are working on modernizing that process. A more modern practice is to mill a cooling channel in the walls of the combustion chamber and the nozzle, and then use a copper or a nickel alloy to close it off, and then that will be the inner wall of the chamber. Copper and nickel alloys are used because of their ability to transfer heat from the walls into the coolant, thanks to their high thermal conductivity. Now you might be asking, doesn't that boil the fuel before it reaches the chamber? Yeah, it sure can. And this process of boiling the fuel can actually be used to spin the turbines to run the pumps of the engines. This is what the expander cycle is. It harnesses the energy of the thermal expansion of the fuel going from liquid to gas. It is extremely efficient, but it is limited by the amount of available heat. We'll talk more about the expander cycle in an upcoming video where we go over pretty much all of the cycle types and talk about their pros and cons. Most engines use the fuel as coolant, but oxidizer could be used as well. But a fun little thing to note is when cryogenic propellants are used, the outside walls of the rocket nozzles can be unbelievably cold, while the inside of the walls are scorching hot. Talk about a temperature gradient. Check out this video of an RS-25 running. If you went up and touched the outside of it, your hand would freeze solid. Touch the inside and it'd burn off instantly. It's honestly crazy to me that these two extremes can exist in such close proximity. One of the challenges with regenerative cooling is that the pressure inside the walls needs to actually be higher than the pressure of the combustion inside the chamber. That's right. The tiny little channels flowing cryogenic fluids inside the thin little walls of a rocket nozzle are actually under higher pressure than the main combustion chamber itself. This is because of the fact that the walls are essentially just tubes that feed the injectors, and pressure always flows from high to low. So the injectors always have to have higher pressure than the combustion chamber. But it's just crazy to me that those tiny little passages inside the walls need to handle that really high pressure too. Seems like with such thin walls, it'd be so easy to spring a leak. Well, if a leak does spring, there's some good news. Let's pretend a leak springs on the inner wall of a regenerative cooled chamber. Because the pressure inside the walls are higher than the pressure inside the chamber, all that will happen is fuel will leak in a little and actually provide some additional cooling. Firefly CEO Tom Marcusic explained this to me when I interviewed him at their factory outside of Austin, Texas.
Engines are amazing, and I haven't seen this here as much, but I've seen places where the engine will actually erode itself down to the point where it starts leaking, and then it's happy, and it doesn't go any further. It just like self-regulates.
Yeah, interesting.
Yeah.
But wait, if fuel leaks into the chamber, how would that not just make it explode more and make an even bigger problem? How on earth can that help cool an engine? Well, that brings us to our next method of cooling, film cooling.
Liftoff. We have liftoff.
Another common method of cooling is film cooling. This is where you inject a fluid between the combustion chamber and nozzle surface and the hot combustion gases. Because don't forget, fluids are either gas or liquid. So this can be done in either form with liquid or gaseous propellants. The basic mechanism at play is creating a boundary between the wall and the hot combustion gas that creates a thermal insulation with a cooler fluid in between them. So how exactly do they do this? Well, let's start off with liquid film cooling. One easy way to do liquid film cooling is to literally just have a higher concentration of fuel or oxidizer injectors on the outer perimeter of the injector face. Engineers will almost always use fuel since the main combustion chamber usually runs fuel rich. So there'll be a whole ring of extra fuel flowing around the outer perimeter that won't have the right amount of oxidizer to react with. This will produce a ring of even more fuel-rich combustion, which prevents heat from transferring from the main combustion gases and the walls. But not only that, most of the fuel closer to the walls won't react at all because it won't have any oxidizer to react with. So it actually just travels down along the walls of the combustion chamber in a film, trapped between the combusted gases and the metal walls. And if it is a liquid, it will likely phase change from a liquid to a gas, and then that'll create a vapor boundary layer, as well as absorb some heat energy in the process of phase changing. It's common to actually drill holes in the walls, assuming they're regeneratively cooled, to intentionally leak in some of the fuel, especially in particular hotspots like the throat of the engine. Another weird benefit of using fuel to cool is that you can create a carbon layer in the form of coking along the walls when using a carbon-based fuel like RP1. When you have a fuel-rich combustion, there's a lot of carbon that will be unburnt and can create soot. Just look at the exhaust of the gas generator for the Merlin engine. SpaceX runs the combustion inside the gas generator extremely fuel-rich in order to reduce its temperature so the turbine doesn't melt, like we mentioned before. As a byproduct, you see the exhaust coming out is very, very dark and sooty. This is the same type of soot that can actually stick to the walls of the chamber and often has a bad side effect, which is having that soot attached to the injectors and potentially the cooling holes or slots themselves, which can clog them up. But the soot that sticks to the walls is another thermal barrier that can help. Again, let's hear Tom Markusik explaining that. We also saw great evidence of the soot when we were up close and personal with their Reaver engines, as evidenced by the soot on Tom's face.
Also, with RoxRP propellants, some of the products that condense on the surface of the chamber are beneficial for inhibiting heat transfer to the wall.
Right.
So once you get up above about 1200 psi, that sort of soot carbon layer starts to come off. So it kind of runs away. Your cooling problems get worse very kind of precipitously as you go over that mark. It's not just 100 psi is a little bit different because your soot goes away and now you've got much more heat transfer to the wall. So there are other factors that play into what's going on in there.
So the coking on the combustion chamber can almost aid as like an insulating barrier?
Oh, it absolutely does. It's a big,
really?
it's really effective thermal barrier coating for free.
Really?
So all that soot you saw in my face and in that chamber, that's great for thermal barrier coating.
By the way, if you haven't seen this interview with Tom, I highly recommend it. Tom is literally a rocket doctor, after all, having a PhD in mechanical and aerospace engineering. So it's packed full of great knowledge. But back to the Merlin engine with that really dark, fuel-rich exhaust from the gas generator. There's another thing we can do with that exhaust. We can use the gas itself to film cool some of the nozzle. But there are a few caveats. You obviously notice that on the sea level Merlins, they are just dumping that exhaust overboard. So it doesn't seem like they're cooling with that exhaust gas at all. But if we pop over to the vacuum optimized Merlin, we can see they do something different with their gas generator exhaust. It isn't just simply dumped overboard. Instead, that turbine exhaust gas is pumped into the nozzle extension that makes the engine optimized for use in a vacuum. In order to understand why this makes sense, we do need to remember something about a nozzle. As it expands after the throat, the exhaust gets cooler and lower pressure the further down the nozzle you go. So keep this in mind when we think about where we can pump in that turbine exhaust gas. It has to be far enough down a nozzle where it's both higher pressure than the main combustion exhaust, and it also needs to be at a point where the amount of heat it needs to protect the nozzle from can successfully be insulated by the film cooling of the turbine exhaust gas, as regenerative cooling is often terminated at that point. Some other engines that did film cooling with their turbine exhaust are the engines on the Saturn V. Both of them, actually. The F1 and the J2 utilize turbine exhaust film cooling to keep the lower portions of their nozzles cool. In the case of the J2, it still utilized regen cooling below the manifold, but the F1 stopped doing regen cooling at the manifold because the film cooling was enough to keep the rest of the nozzle from melting. There's a really fun and distinct thing to notice when the F1s were running. Notice the bright orange flame front doesn't actually start at the end of the nozzle. There's this weird dark bit dancing around between the flame and the nozzle exit. That's the turbine exhaust film cooling gas. Because it's so fuel rich, it takes a moment for it to find oxygen to burn with and ignite. This of course doesn't happen until outside the engine, when it eventually will react with oxygen in our atmosphere. But what's confusing is we can see a little bit of this in a closed cycle rocket engine that doesn't have a gas generator and therefore doesn't dump the exhaust gas into the nozzle. I mean, check out the RD-180 on the Atlas V. Notice there's little dark spikes leaving the nozzle. It's kind of similar to the F1. That's from the fuel-rich film cooling and not gas generator exhaust soot. It's not as prominent, but it's still quite noticeable. But you might actually notice some dark spots in some other engines, such as the vacuum-optimized Merlin engine or Rocket Lab's vacuum-optimized Rutherford engine. Rocket Lab founder, CEO, and CTO Peter Beck was talking to me about this in a recent interview.
You know, most engines will run some film cooling, so there's a small amount of film cooling. And in fact, if you look at, you can look at just about any rocket engine on an upper stage on a refractory metal alloy nozzle, like a niobium nozzle, you can see the dark spots. So if you'll notice it's kind of on a nozzle, there's this kind of dark spots that run around the periphery. Well, those are actually the locations of the injectors up in the thrust chamber, and that's where the film cooling injector kind of lies, is in line with one of those dark spots.
But notice the vacuum optimized Merlin and vacuum optimized Rutherford look a little different than the others. When they're running in space, their nozzle extensions glow bright red. What the heck is going on here? That is just the metal getting really hot and then radiating that heat out into space. Well, this is another viable option to keep your rocket engine from melting. Don't forget, there's a difference between radiative heat transfer and conductive or convective heat transfer. Since there's no atmosphere in space, there isn't any air to pick up and conduct or convect the heat. So it's not like you can just run a fan over your engine to keep it cool and expect it to wick heat away. The only option here is to radiate the heat away. Unlike convection or conduction, radiation doesn't need matter to transfer heat, just like how the sun transfers heat through the vacuum of space via radiation. The nozzle extension in the vacuum-optimized Merlin and Rutherford are made out of a very thin metal, usually some alloy, such as niobium alloy or some other material that can withstand high heat loads. Now, the problem with, say, the niobium nozzle extension is it's very thin and relatively fragile. But even more problematic is how reactive niobium is to oxygen. This means engines with niobium can really only operate in a vacuum, and it also means their manufacturing is much more difficult. Another famous engine that used a niobium nozzle extension was the AJ-10 on the Apollo service module. That dark part is niobium. And it's a good thing that engine worked well, because otherwise it could have left Apollo astronauts stranded orbiting the moon. Okay, I think that pretty much does it. I'm sure there's some other fun tricks propulsion engineers employ, but that's really the main ones. And it's really fun to see how engineers choose which systems work best for their engines. But I think to review this topic best, let's just look at the vacuum optimized Merlin one more time, because it employs almost every type of cooling. At the gas generator, we see both heat sink tactics and a very fuel-rich exhaust employed. This makes sense because the other forms of cooling can't be utilized on spinning turbines. You just have to use high temperature metals and then lower the exhaust temperatures to make sure it doesn't get hotter than those metals can handle. SpaceX uses regenerative cooling for the chamber walls, throat, and the first bit of the nozzle. Then inside the engine, they employ some film cooling with additional fuel in the chamber and near the throat. They also use film cooling from the gas generator exhaust at the nozzle extension when the regenerative cooling channels end. But in addition to the film cooling, the nozzle extension also radiates additional heat away by using a thin but high temperature niobium alloy. The only form of cooling the vacuum optimized Merlin doesn't appear to use is ablative cooling. But considering the upper stages are only used once, this is one engine that could probably get away with a little ablative cooling in a spot if they needed to. I love all these little tricks that engineers have figured out to keep rocket engines from melting. It blows my mind that regen cooling works for some reason, and also that you can use exhaust gas from the turbine to film cool your nozzle too. For some reason, both of those things just seem kind of crazy, and it's amazing that they work so well. Let me know if you have any other questions, or maybe let me know if you learned something cool, literally, or if you have ideas for upcoming videos in the comments below. I owe a huge thank you to my Patreon supporters for helping make videos like this possible. If you want to help me continue to do what I do, head on over to patreon.com/everydayastronaut, where you'll gain access to our exclusive Discord channel, some exclusive live streams, and even early access to some videos as well. Again, that's patreon.com/everydayastronaut. And while you're online, be sure and head over to our web store for shirts like this, the brand new RD-171 shirt, that if you watched the Soviet rocket engine video, you know this is one of the coolest engines. This is now one of my favorite shirts. But be sure and check out some of our other cool stuff too, such as our Space Shuttle ejection hoodie, our brand new RS-25 shirt, or our schematics collection, or our Future Martian shirt. Lots of really cool stuff over at everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.